This is Algebra 2, Lesson 57. We're on page 245. This is a chemistry lesson. It's an introduction to what's called the ideal gas laws. Okay, the best way to teach you about gas laws is to blow up a balloon because it demonstrates gas. I'm actually going to put a gas, inside the balloon. What will happen to the balloon when I put gas in the balloon? It will expand. That's right. Have y'all done gas laws in chemistry?
No. We did it in music.
You did?
No.
Okay, so it expands, right? Why does it expand? What does the gas do to the surface of the balloon? It puts pressure on it. That is correct. And the pressure comes from the movement of the molecules in the gas. Now, what would happen if I left this balloon overnight? What would happen to the size of the balloon? It gets smaller. You know why? The gas particles settle down and they compress. They become smaller. Right. Now, what would happen if I continued to blow this balloon up? It will get bigger and bigger and bigger until... I knew you would be the one. No, yes, it would pop. Right? It would pop. I'm not going to let it pop. But that is the greatest example of the property of ideal gas. Truth be said, there's no real ideal state of a gas. There's really not one. However, we do have this formula such that if we get gases in a state where this is true, this formula is true, then you can compress the gas. And that's what happens as the balloon shrivels back up. So here's the formula for ideal gas law. PV equals nRT. PV equals nRT. That's the ideal gas. That's the equation for ideal gas. All right. P is pressure. P is the pressure. Look at your textbook on page 245. It gives you some measurements for each one of these. The pressure is typically measured in newtons per square meter. Sometimes it's in atmospheres. So atmos is the abbreviation for atmospheres. In your higher level chemistries, it's probably going to be in newtons per square meter. Sometimes it's in atmospheres. I would say it's more times than not, it's going to be in newtons. Newtons is the big N. All right. This V is volume. All right, so volume is the same across the board. Liters, milliliters, that type of measurement. All right. Think of a 2-liter bottle of Coke. Even though this is a gas, right? Coke is a liquid, although it creates gas, right? And does anybody know what N is? Do y'all use this in chemistry? Oh, wait, y'all haven't done moles. Yes. You've done moles. Okay, so this represents the number of moles. The R, it's a constant. Almost like pi is a constant. Okay, well, it is like pi is a constant. But it's not 3.14, it's like 8 point. Well, you don't have to worry about that right now. It's like 8.314. And then T is the temperature. Normally, we look at temperature in terms of degrees Celsius or degrees Fahrenheit. But in your higher level chemistries, temperature is measured in kelvins. right? The measure for temperature is in kelvins. Because we are not in a science class, we are in a math class, we are simply going to look at the equation and not have to figure out what an ideal gas, what a gas would be like in an ideal situation. Which, remember there, we're going to, for this lesson, we're going to ignore the N and the R. All right, so we're going to ignore that. Actually, what we're going to do is we're going to say that holds constant. We're not really ignoring it. You cannot really ignore it, although it's not even taught in the book at this point. If we look at the formula, we're going to say this part of two gases are the exact same. So I'm really dividing by T on both sides, and I'm setting two gases equal to one another and saying what is the equivalent ideal states of two gases. So you need to memorize PV over T, right? What do we need to memorize? PV over T. Because PV over T for one gas, we want it to be equivalent to PV over T of a second gas. And so this is the formula that we will use for this lesson. But I think it's important for us to understand we're really saying that the number of moles and the constants are equal. So we're not really ignoring it. We're just setting the two equal. So here's the key formula for this lesson. Now, as we read, these are all in word problems, so you have to know if they say kelvins, it's pressure. If they say, kelvins is temperature. If they say atmospheres, it's pressure. Or if they say newtons per square meter, it's pressure. If they say liters, then you have to know that that's like volume. Okay, so you're going to have to know which measure goes with which one of these variables. All right. Also, there's a word in your book. Look right under it says for temperature kelvins on page 245. It says a Pascal. You see that? A Pascal, abbreviated PA, bottom of page 245. I do think Pascal is used in chemistry. I'm pretty sure, my oldest is a chemical engineer, so I hear all this kind of stuff, right? My youngest is going into chemical engineering. All right, so a Pascal, it says, is the SI metric. Do you see that? Does everybody see that? All right, I don't think we say this enough at, probably in our science classes, but SI, most of your higher level, your college level sciences are going to be in the metric system. And SI is sort of like, is the acceptable measure for like pressure, or the acceptable measure for like temperature. Like the SI, you learned about it. I love it. I love that you learned about it. All right, so it's mostly metric in college. Okay, you'll have SIs in both chemistry and physics, which is crazy because most of what you learn up to this point is the English system. But in college, you're going to do mostly metric, like meters per second. We don't do miles per hour. It's meters per second. Okay. So let's, I'm glad you guys know about the SI. I'm so excited. You must have learned about that in chemistry.
Yep.
Excellent. Excellent. All right, now let's go to example 57.1. All right, and we're remembering PV over T for 1 equals PV over T for a second gas. Okay, 4 liters, what is that? Is that pressure, volume, or temperature? Volume. So I'm going to write that where volume is in the first equation. 4 liters of an ideal gas at a temperature, of course it tells you temperature, that's your T, 800 kelvins, has a pressure, it told you, of 100 newtons per square meter. All right, so that's the ideal state of this gas. If the volume, now we're going to actually change something in the gas, and we're going to have to calculate one of the other variables. So if the volume of the gas, of this ideal gas, were increased to 10 liters, what is the 10 liters? Volume. And the temperature reduced to 600 kelvins, then what should be the resultant pressure for it to stay in this ideal state? So when you change the volume, when you change the temperature, it's got to change the pressure. All right, how do you think we solve for this? Yes, Mackenzie?
Can we simplify first?
Okay, simplify. How do you want to simplify?
Well, that would be 1/2 because 100 times 4 is 400, which is half of it.
You can simplify, yes?
And then the 10 over 600, you can just cross out through.
So it's okay. Does anybody already know what the temperature has to be? I mean, the pressure has to be 30, half of it. Okay, you could cross multiply. 60 equals, and then divide by 2. 30, and what was the measure? Newtons. And you can just write a big N for newtons. That means newtons per square meter. Okay. I could have just multiplied everything out, cross multiplied. I didn't have to simplify, but you can simplify before you multiply. All right? So this is a big lesson, but easy problems, right? Because all we're doing is plugging those numbers in and solving for the one variable that's left. All right, let's look at example 2. The initial pressure of a quantity of ideal gas is 400 newtons. So that's the pressure. 400 newtons per square meter. And the initial temperature is 1200 kelvins. Does it say anything about the volume? The volume is held constant. Okay. When something is held constant, does it change?
No.
So will it affect PV over T? So just ignore it. Well, we're not ignoring it. We're just saying it doesn't affect the multiplication because we'd be multiplying by the same value on both sides. All right. What was the pressure? That's what we're solving for in the second one. What was the pressure if the temperature was decreased to 900 kelvins? All right, so this is what? 1 over 3. 1 over 3 equals P sub 2 over 900. What's P sub 2? What did the pressure have to be reduced to? 300 kelvins. Newtons per square meter. Newtons. Yes, the temperature was kelvins. All right, so when something is held constant, it does not change the value on either side. So you don't even have to consider it in your equation.
Would the units only matter if it was said it was like the temperature was 112 kelvins and then the temperature was something Fahrenheit, and that was the only way. That would be the only way the units would matter because you have to.
That's correct, and they're never going to do that. They're never going to change your units. Now, when you get to college, probably in chemistry, they absolutely are going to change it. And even in high school physics, when I taught Thomas high school physics, the problem may have been given in English units, but you had to give the answer in metric in the SI. Is that a question?
Are they ever gonna give us T or the temperature as the variable, or not as the variable?
They may, yes.
Okay.
They may say, what would the
What
temperature
should it be?
Right, what should the temperature be? All right, look at 57.3. Now the temperature is held constant. So what do I not have to be concerned about? So it's just going to be PV equals PV. Make sense? The original pressure was 7 atmospheres and the original volume was 42 liters. If the volume was reduced to 10 liters, what was the pressure? What do I do? Yes.
I'm just wondering, are we only defining pressure?
That's it.
No.
No.
All these problems, because that's what they seem to be doing.
Not necessarily. Sometimes you may be solving for volume. Sometimes you may be solving for temperature. You just divide by 10, right? What's the pressure? 29.4 atmospheres. This wasn't in atmospheres. Okay, so it's just a simple formula, PV over T. If something is held constant, you can leave it out of the equation. All right?